So welcome to the Post-Glover 2020 Summer Webinar Series. This is installment number 4. And today we'll be discussing the basics of dynamic braking resistors. What the heck? It's not working. Oh, come on. 1 minute, please. Someone turn this off. Did it go? Okay. What happened? Okay. Okay, sorry about that. Okay, so my name is Steve Fisher. I am one of the Post-Glover application engineers, regional sales managers. I've been here at Post-Glover for over 15 years, and I graduated with a BS in mechanical engineering from the University of Notre Dame, who, by the way, I'm hoping will have a football season, but we'll see how that goes. There's a picture of me over there on the right that was taken recently by one of the people in our plant here. And this is a picture of me when I was a young student in 2nd grade, anxiously awaiting my lesson on dynamic braking resistors. Okay, so what are we going to hopefully learn today? Well, first of all, we want to talk about when you need a dynamic braking resistor. And we're also going to discuss how the dynamic braking resistor works with your variable frequency drive. And we're also going to show you how to choose the correct ratings for your dynamic braking resistor. And that's pretty much the ohm rating and the watt rating that we need. And I also would like to mention that during this presentation, up on the right-hand corner, there will be some icons there. If you click the red arrow, it'll pop out, and you can type in a question in there and hit submit, and it'll send it to us. And as we're going through the seminar, we will either reply to you with an answer. If it's a simple question, at the end of the seminar, we will have a question and answer session, at which time we will answer some of the questions if there's too many, or if your answer takes an attachment associated with it or a long explanation, we will reply to your question via email at a later date. Okay, so before we get started, I would just want to give you a quick cheat sheet of terms that may or may not be used during the presentation. Variable frequency drives are what are typically used with our dynamic braking resistors. So it may say drive, I may call it a drive. In the handouts, I wrote VFD just to save space. So both of those mean variable frequency drive. Of course, I'm talking about dynamic braking resistors, and I may just call it a dynamic brake. I may call it a braking resistor. And I know, again, in the handouts, or on the presentation, it says DBR, and I might call it a DB while I'm speaking. One of the things that dynamic brakes are measured in is resistance, and that will be the capital letter R if it's in a equation. And the symbol for resistance is ohms, and it's shown by this omega sign. And when we're talking about power, power is measured in watts, which is that capital W. And if it's 1,000 watts, it's known as a kilowatt, which is a kW. Okay, so we're also why are dynamic braking resistors actually needed? Well, as you all pretty much know, as you're working with your variable frequency drive, you're getting AC signal from your grid. It goes into the variable frequency drive. The drive turns that nice waved AC signal into a bunch of little pulsed DC signals. They're all kind of stacked up, so it makes it look very similar to that AC wave. However, the variable frequency drive can then vary the frequency of that, and your motor can go slower and faster. So the drive is sending that signal to the motor to make it go slower or faster. However, when that motor is stopped or braked, or if it's overhauling, it sends energy back to the variable frequency drive, which is shown by this backward arrow here. So the variable frequency drive basically doesn't like that, and it causes the DC bus in that variable frequency drive to increase. And if that DC bus voltage increases too much, you're going to get a over voltage trip in your variable frequency drive. So then it takes some of that energy and it diverts it onto this dynamic braking resistor, which then turns that energy into heat. So how does that work? So I've made a very simple little diagram here. So all these parts here there's many parts within a variable frequency drive. They're all electronic, and I've just shown a few of them here. But as we talked about, when the motor stops, or is overhauling, it regenerates all that energy back to the drive. The drive doesn't like that, and as it's sending that energy back, the voltage on that DC bus increases. When the DC bus increases too much, it may cause the variable frequency drive to trip on over voltage. So there's another part of this called the chopper, or sometimes called the transducer. It will monitor that voltage, and when it gets to a certain point, it decides it's time to divert that energy over to the dynamic braking resistor. And then it does that, and that keeps the variable frequency drive from tripping on over voltage. And then again, that dynamic braking resistor then takes that energy that's diverted to it, and it turns it into heat. So as I said, the transducer is monitoring that voltage. So we were wondering, what's that great voltage where it starts to divert it to the dynamic braking resistor? So if you have a 240 volt or a 208 volt variable frequency drive, typically the voltage is 375 volts. If it's a 480 volt series, it's a 750 volt. And if it's a 600 volt or 575 volt variable frequency drive, when it hits 938 volts or so, that's when it diverts it to the dynamic braking resistor. And those are all pretty standard. They can be adjusted with some drives, but that's the standard value. Okay, so let's talk about some of the pros and cons of dynamic braking resistors. First of all, some of the advantages are that they are very simple and they're low cost. So as I said, the variable frequency drive is connected, the dynamic braking resistor is connected to the variable frequency drive DC bus. So there's going to be an in and an out on the resistor. We will supply a set of terminal blocks. That's 2 points. You land on each one. If you hook it up backward, it doesn't matter because a resistor doesn't have any polarity. So you can go frontward or backward, it doesn't matter. So they're simple to install. You just basically put 2 wires on it. And they are very low cost as compared to, we'll talk about regen a little bit later, but some of the advantages, again, it takes all that energy off of that variable frequency drives so that it doesn't trip, and it dissipates that into heat. And you can use a dynamic braking resistor for any application. You can use it for a decelerating or braking load or for an overhauling load. You just have to get the right parameters in it, but it doesn't matter. If you buy one, it doesn't matter what you use it for, what application you use it for. So some of the disadvantages of dynamic braking resistors is that energy that's going from the variable frequency drive to the resistor is basically just lost as heat. And the other thing is that as it turns this into heat, you have to think about your overheating. So your environment that you put this in is sometimes critical. You probably don't want to put this in an air-conditioned room. For instance, you don't want to put it with your server in the same room as your server for your computer. You don't want to put it sometimes inside a panel with all kind of electronics. If you put it in there, sometimes it'll overheat and it'll cause issues with those electronics. The other thing is you have to not just your environment, but you have to think about location. Even though you're putting it out in the shop and you don't care about heat, you have to think about what it's around. So you don't want to put it under your cable tray or a conduit or something like that, because that heat will possibly cause issues with your wiring and your cable tray or your conduit, and may cause a fire or other issues. The other thing you have to think about is when people are laying out their assembly, they think about where to put the variable frequency drive because they're big. sometimes people forget about the dynamic braking resistor. So you have to think about where you're going to put that also. Okay, so we're going to go to poll question number 1. And the poll question is, which image on the poll to the right was based on the likeness of Steve Fisher? Wait a minute, not that kind of poll. I'm sorry. Rob, can you cue up the actual poll question for us, please? All right. I just want to let you know too that the likeness image of me, I did that while I was in college. And of course, since I was in college, I was not considered a professional. So I didn't get to reap all the great rewards and money that came with that using my likeness for that poll. So, okay, so let's talk about our dynamic braking resistors. Why are ohms and watts important? So I'm showing here, there's 2 different dynamic braking resistors. There's one on the left and there's one on the right. This one on the left is a very small wattage resistor and will typically be used for a small horsepower variable frequency drive. The one on the right is a very large wattage resistor and will typically be used for a very large variable frequency horsepower drive. So as you can imagine, the one on the left is going to have small wires in it and it's going to carry a very low amount of current. And the one on the right typically has large plates in it and it will carry a high amount of current. And as the lower the amount of current you're carrying in a wire, the higher the resistance is. So typically your lower horsepower dynamic braking resistors have a higher ohm rating, and your higher horsepower variable frequency drive require a dynamic braking resistor with a lower ohm rating. We'll talk about that and you'll understand why in a little bit. Okay, so I've shown here a very simple diagram. I try to get a visual for people to understand. Since you can't see electricity, I know I've felt it more than once in my life. You can't really see it, so I try to give a visual so something people can actually understand in their daily life. So I'm showing here your motor, and as that is overhauling or braking, it's sending regen energy from the motor into the DC bus, as I spoke about before. So you think of that DC bus as a DC bus voltage sink. So as you can see, I've drawn this rectangle here. This is depicting, think of your kitchen sink or your sink in your laundry room or whatever as something that's going to be holding water, okay? So as this motor is dumping energy into this sink, think of that as the amount of water, that sink is slowly filling up. So it fills up to it's a quarter full, half full. When it gets to a certain point, about 3/4 full, or whatever that number is, there's something in the variable frequency drive called the chopper. It senses this, and it thinks about, well, I'm almost full, past my voltage level. So if you remember that table, this is like could be around 750 volts for a 40-volt drive. So it doesn't want it to get too high, to like 800 volts, because then it will trip on over voltage. So when it gets to a certain level, it decides to open up the drain, or basically drain it to the dynamic braking resistor. So I've shown here 2 different drains on this picture. Of course, it's only going to have one drain in reality, but I've showed this to try to give you an explanation of what you want to be doing. So if you look at this, this is a very small drain. This is going to resist the flow of that water a lot. And the drain on the right is a very large drain, and it's not going to resist very much flow of this water. So in essence, you can think of this one that's resisting a lot as a high ohm resistor, 100 ohms. And the one on the right, it's not resisting much flow at all as a low ohm, or like for instance, a 1 ohm resistor. So the other thing to think about is, depending on which one of these drains we open, if you have a high ohm resistor, it's not going to let much of this water through at once. And this is going to let a lot of water through all at once. So think of that water rushing through here as the amount of current running through this pipe or this drain. So this one's also, obviously it has a higher ohm value. It's going to have a lot less current. This with a low ohm value is going to have a lot more current. Okay, so here's a little visual here. On the left quadrant here, we have on these two sides, this is a quarter horsepower drive. And on the right, this is a 250 horsepower drive. So obviously the sink in your quarter horsepower drive is going to be very small, like the size of a thimble maybe. And the energy going into that's going to be very slow. It's like trickling out of this water dropper. And conversely, this DC bus sink on a very large drive is going to be a very large sink, like this industrial sink here. And the energy flowing into it is going to be like on a fire hose, a whole bunch all at once. And also the DC bus inside each of these drives is going to be represented by something very small like this wire in a quarter horsepower drive, or the 250 horsepower drive can handle a lot of current, as shown kind of like by these 3 pieces of copper bus. So getting back to something similar to the drawing I had before, think of this as your very small quarter horsepower motor. It's dumping energy in very slowly, and this very large motor is dumping energy in here very quickly, like with this fire hose. So if you're filling the sink up, of course, if you have a small motor, the sink would be smaller, but if you're filling the sink up very slowly, you're going to want a resistor that's draining it very slowly. And if you're filling this up really quickly, you're going to have to drain it with this lower ohm resistor, because you have to drain it faster than you're filling it up. Okay, so back to this quadrant here. So I'm now showing, again, we have the same sinks, and they're being filled up. On the quarter horsepower drive, you have a high resistance resistor, so you're resisting the flow here. And since you can't get much water through here, this is going to be a very low current, because again, that bus can only handle a little bit of current. Whereas this resistor here has a big conduit. There's going to be a whole lot of current running through this one. And of course, if you're only draining this small little thimble here, your resistor can be a lot smaller. When you have this big, huge sink, you're going to need a much larger resistor. So again, that 250 horsepower drive is going to have lower ohms, less resistance of flow. It's going to handle more amperage, and you're going to need a bigger dynamic braking resistor. This quarter horsepower drive has a smaller resistor, more resistance to flow, and it'll handle less amperage. Okay, so before I just said you have to have a lot of resistance or a little resistance. Well, you have to actually pick the right number. So how do we choose our resistance? So every drive manufacturer has what's called a minimum resistance rating. And that's based on the maximum current that the chopper transistor can handle. And of course, it depends also on the turn on voltage, which again, if it's a 480 volt, it's going to be 760 volts. So the minimum resistance is your voltage that your DC bus turns on and your maximum current that it can handle, divided by the maximum current it can handle. So as I said before, you have a lot of resistance you're going to handle. Since resistance and current are inversely proportional in this equation, the more resistance you have, the less your current is going to be. And if your resistance is very small, you're going to be able to handle more current. And again, if you go below that minimum resistance, if you have too much resistance in your resistor, you won't drain fast enough. Or I'm sorry, you're going to drain too quickly, and you're going to trip your variable frequency drive will trip on overcurrent, because too much current will be running through it when it drains. Okay, so there's also, besides the minimum resistance, there's also a maximum resistance, and that is calculated basically just by using a calculation. It doesn't come from the drive manufacturer, but you have to know your voltage of your DC bus turn on voltage and the horsepower of your drive. So the larger the horsepower, again, these are inversely proportional. So the larger your horsepower, the lower your maximum resistance is going to be. There's also some factors of braking torque, and there's some motor efficiencies. We're going to not talk about those this time. I'm going to do another webinar. I'm sorry, post-Glover, somebody at post-Glover will do another webinar in a few months, and we'll get into some more of this. But so basically, the resistance and horsepower are also inversely proportional. And if you go above that maximum resistance, you're going to trip on over voltage because you won't be draining your variable frequency drive of its energy quick enough. So you'll have too much voltage built up and you'll have an over voltage trip. The other thing that can happen is it can extend your time of, say you have a conveyor and you're going and you want to stop it in 5 feet. If you're not draining quick enough, it may take it too long to stop. So you have to make sure, even though you don't trip, it might affect how your whole application is working. Okay, so we also have to choose the actual wattage or kilowatts of our dynamic braking resistor. And that depends on a few different variables. One is the horsepower of the variable frequency drive. So if you remember, the larger horsepower motor needed a very large dynamic braking resistor. It also depends on the duty cycle, which we'll discuss in a little bit. I'll discuss what that is, but essentially it's how often are you draining this? How often are you turning on your dynamic, dumping power into your dynamic braking resistor? And it also depends on what kind of load is coming back to the variable frequency drive. There's a braking or decelerating load, and there's also an overhauling load. And again, we'll talk about those in a little bit. So this is all determined by a formula, and it's very simply the power, the maximum power of your drive times your duty cycle, which we'll discuss a little bit. And there's also a safety factor involved. Post-Glover uses a 20% safety factor that is used in case you don't have exactly know your application. We put a little bit of extra wattage in there so you don't overheat your resistor. Also, sometimes if you think you're going to be on for 10 seconds and off for 30, if you ramp up production, sometimes you're only off for 25. So you need a little bit more wattage. So there are two different kinds of loads. Again, we'll talk about this in a second, but there's an overhauling load where you take your power times your duty times your safety factor. And if it's a braking type of load, you'll have a decelerating load. So you take half of that value. So you're taking half of your power of your drive times your duty times your safety factor. Okay, so now it's time for poll question number 2. Rob will set that up. Okay. And there's our shorting poll results. Okay, so as I said before, when you're draining this energy into the dynamic braking resistor, the dynamic braking resistor is taking that and turning it into heat. So you have to remember that heat can be an issue here. So one of the things we have to make sure that you do is when you figure out what wattage you need, you have to make sure that the wattage of your dynamic braking resistor is greater than or equal to the actual wattage that you need, that you calculated. If you don't do this, what will happen is if you, for instance, if you need a 10,000 watt resistor, you think you need a 10,000 watt, but you only buy a 5,000 watt to save a little money in space, that resistor will get extremely hot. And as you can see here, my buddy Bob here bought a 5,000 watt resistor when he needed actually a 10,000 watt. And now he's got a basically something to cook his hamburgers on. So I'm sure a lot of you have actually had this happen to you where the dynamic braking resistor gets really, really hot, and sometimes it runs cooler, and that's pretty much based on the wattage that you choose in your dynamic braking resistor. So think of putting a 200 amps through a 20 amp wire in your wall. That the wire can handle that amperage for a very short time, but after that, what will happen is the insulation will start to break down, and it will actually cause a fire or damage something. So you have to think about, if you under wattage, you don't get enough wattage in your resistor, you can cause issues as not only just overheating, but you can cause a fire hazard possibly. The other thing is it may not cause a fire and you may not worry about the heat, but if you put too much through it, it will also reduce the life of your resistor after time. So instead of getting whatever 50 years worth out of your resistor, it may only last for 5 years. To prevent issues of overheating, Post Glover sends a thermal switch, standard with all of our dynamic braking resistors, and those are going to be used for protection. And here's a picture of it here. So this is a very small dynamic braking resistor we have. There's the thermal switch right here. You can wire this right up, and when the temperature gets too hot, that'll open up the contacts in this normally closed thermal switch here. And then this will typically be wired to the enable circuit in your variable frequency drive. And then if that switch opens, it cuts off that, and then the variable frequency drive will turn off. So again, by overheating, you could actually turn off your whole, whatever your application is doing, your conveyor belt or your mixer or whatever is going on, is going to stop. So the other thing I do want to mention is this thermal switch. It works on the amount of heat that sees the temperature. It's a temperature switch. So as we all know, the heat radiates out of this resistor, and then the hot air that's around it rises. So you have to think, when we send you a dynamic braking resistor, we'll show you a little sheet in there. It shows you how to mount these. You have to make sure you don't put this thermal switch directly pointing upward or right on top of the resistor, because all the heat from that resistor will then hit that switch, and you could cause nuisance tripping occasionally. All right, so now we're going to talk about our different types of loads. As you may recall, we talked about overhauling loads and braking loads. So an overhauling load is a load that is driving the motor, and it essentially turns that motor into a generator. So that would be like a constant load over a period of time. For instance, an elevator or a crane or a hoist. It's taking that load, and you get constant descents or pulling characteristics, and it's putting that constant power, throwing that back onto the variable frequency drive. I'm sorry. And as we have an overhauling load, as you can see here, you have the braking power, and it is constant. You have that same amount of power going for however much time you have for that braking cycle. So the wattage that you need for an overhauling type of load is taken by the peak watts, which is essentially the horsepower of your drive, times your duty cycle, which we'll talk about in a second. And again, we have a safety factor of 20%, or we multiply it by 1.2. Your duty cycle is defined as the amount of time on, which is this, divided by the total cycle times, which is the time between when you start this and when you start the first time, when you start the second time. So if you look at this picture, this braking time, let's just say this is 10 seconds, and this total cycle time is, we'll just say it's 25 seconds. So the duty cycle here would be 10 divided by 25, which would be 40%. Okay, so there's also what's called a decelerating load, or braking, dynamic braking load. In this type of load, the current actually decays. So if you think about this, when I talked about it, it was called braking. So think of you driving in your car going 100 miles an hour. When you're going 100 miles an hour, you hit your brake, you're spending a lot of energy to slow down that car. And as your car slows down, as your load slows down, by the time you get to be going about 1 mile an hour, you don't have to hit your brake as hard, and you're not taking as much energy to stop that car. So Again, you need a lot of power when you start to stop, when you start slowing down, and by the time you're totally stopped, you don't need as much power. So this is indicative of like an emergency stop applications, which I would say most of the dynamic brakes out there are used for emergency stop applications. Centrifuges or spinning devices, punching machines are other examples. So as you show here, see how this is a triangle. Before we had, when we had the overhauling load, we showed a rectangle. That triangle, the area under the curve here for this triangle is half as big as the area that we had for that rectangle. So that's why we're taking 1/2 the value of the peak watts, which is right here, times the duty cycle. Again, the time off divided by the total time, times your 1.2 safety factor. Another way to look at this is this is the amount of power you have when you start. This is the amount of power which is 0 when you stop. That 1/2 is the average of this two, this maximum and this minimum. One other thing I would like to note about duty cycle is that the resistor will begin to saturate temperature-wise in around 100 seconds to 120 seconds. It's somewhat dependent on a few different things, like how the resistor is mounted, where it is, how close they are to other plates, the material it's made out of. But in essence, you can use either 100 seconds or 120 seconds, okay? So if you think about this, if I have an application where I'm overhauling something all day long on Sunday, so I'm overhauling this load 24 hours straight, and then I turn my load off, and then I don't overhaul anything for the next 6 days. So Monday through Saturday, I'm not turning on. And then Sunday, I'm overhauling all day long again. You can't think of that as being around 15% duty cycle because you're only using this 1 day out of 7 days. Again, that resistor will saturate in about 100 seconds to 120 seconds. So what you have to do, you have to look at your worst case scenario, take a snapshot in that 100 seconds and look at that. So what we would do is we'd go to noon at 12 o'clock, look at that 120 second snapshot and say, during that 120 seconds, it was on continuously. So this is really a continuous load and not a 15% duty cycle, as you could think of it as. Okay, so let's go over some examples here to actually figure out which dynamic braking resistor we need for a few different applications. So my first application is an overhauling type of load. The variable frequency drive I have is 480 volts, and it's a 10 horsepower drive. Okay, in this application, I am going to be overhauling for 10 seconds, which is shown here. Again, this line is constant straight across here for 10 seconds. And then my dynamic braking resistor is not engaged. And then I rest for 30 seconds, and then I do the cycle all over again, overhauling for 10 seconds, turn off, rest for a while. Okay, so I've looked at I figured out that my minimum resistance from my variable frequency drive manufacturer is 35 ohms. And I punched my calculation and I found out that my maximum resistance is 90 ohms. So the resistor I choose has to be between 35 and 90. My total cycle time is, again, the time that it's on is 10 seconds, plus the time that it's off, which is just 30 seconds, or 40 seconds. Or you can think of it as the cycle time is there's every 40 seconds, you're going to be turning on your dynamic braking resistor. So since your time on is 10 seconds, your total time is 40 seconds, your duty cycle is 10 over 40, which is 25%. Okay, so I have 25% duty cycle. My peak wattage is, you can take your horsepower. Some drives are done by horsepower, some are sized by actual watts. So you could have a 2.2 kilowatt resistor, or it could be certain horsepower. So if it's in horsepower, you want to convert that horsepower into watts. So you take your horsepower times 746, which gives you 7,460 watts. 746 is just the conversion factor. It's similar to converting millimeters to inches. You're just finding that number, that 2.54, and it's a constant number. I could go over all the math, but I don't want to bore you any more than I already have. So the wattage in your overhauling type application, again, as I had from your equation before, is your peak wattage, which is 7460, which I just calculated. So that's shown right here on this graph. 7.46 kilowatts, times your duty cycle, which is 25%, which we figured out, times your 1.2 safety factor. So my total overhauling wattage I need for this application is 2,240 watts, or 2.24 kilowatts. So I'm going to choose a 50 ohm resistor, which was between the minimum and the maximum, and my wattage is going to be 2,240 watts. Okay, so my second example, I'm going to use the same variable frequency drive. I'm going to have the same duty cycle, which is on 10 seconds, off 30 seconds. However, this time I'm going to be it's going to be braking. So as you can see here, this is decelerating. So the area under this curve is depicted by this triangle. In example one, it was this rectangle here. And as you can see, since this is this triangle, the area under this curve is half as much as it was before. So again, I have the same duty cycle. I have the same peak wattage. My braking wattage that I need is 1/2 of the peak wattage times the duty times your safety factor. So that's 1,120 watts. And if you remember from the first example we had, it was 2,240 watts, which is twice as much. So this time I'm going to choose a 50 ohm, 1,120 watt resistor. If I wanted to use that first resistor, I could have done that, use the 2,240 watt resistor. It would still work fine. It would just run a little cooler. And it would also allow you to possibly change your application if you need to later. All right, so those were two very simple examples. I'm going to go over one more example. It's a little more complex, not extremely complex, but a little, and I'll show you how you can use your calculations here. So this time I have a 480 volt drive again, but this time it's 50 horsepower. So I looked up in my manual and I found out that the minimum resistance on this variable frequency drive is 20 ohms. So in this application, I'm going to be overhauling for 20 seconds. So this 20 seconds here, I'm overhauling. Then it's going to take 10 seconds to stop. So it's just shown by this decaying line here. So 10 seconds, it's stopping. Then the application will do its thing for a while for 20 more seconds. Then I'm going to start all over again. So my cycle time is the addition of the overhauling plus the stopping and the time between repeating, 20 plus 10 plus 20. So my cycle time is 50 seconds. So again, I've got that information written up top. My peak wattage is my horsepower, which is 50 times that 746, which is that conversion factor. So my peak power is 37,300 watts, which is shown here on this graph, 37.3 kilowatts. So the total wattage I need for my dynamic braking resistor is going to be the duty cycle for the overhauling, for the wattage I need for the overhauling plus the wattage I need for braking. So here's the overhauling load here. Again, it's overhauling for 20 seconds. So if I were to drop a line straight here, that would be the area in this rectangle. So that's 20 divided by 50 times your peak wattage, 37,300, times your safety factor. Then I have to add the wattage we need for braking. So the wattage you need for braking is shown by this line right here. So again, that's half. The duty cycle is 10 over 50, or 20%, times 37,300, which is your peak watts, times your safety factor. So I crunch all those numbers, I get 22,400 watts. So I have to make sure that my dynamic braking resistor I purchase is at least 22.4 kilowatts. Okay, so I'm going to choose my dynamic braking resistor I need. I know that my resistance has to be greater than or equal to 20 ohms because that was the minimum ohm value for this specific variable frequency drive. And I know that my wattage has to be 22,400 watts. However, I did my calculation for the maximum ohms to keep it from tripping on overcurrent, and that was also 20 ohms. Well, you may think, well, then I'll just get a 20 ohm resistor. That'll work fine. Well, it may work fine, but something you have to remember is there are tolerances in resistors. So you might order a 20 ohm. It might come out to be 19.5 ohms, or it might come out to be 20.5 ohms. The other thing is you have to think about your environment. If you're putting it in a steel mill way up high for a crane, it's going to be extremely hot up there. And as a resistor material heats up, the resistance increases. So the other thing to think about is as you're overhauling for that first 20 seconds, you've got current running through this resistor. That is heating up the resistor elements and is increasing your resistance. So you might start out with a 20 ohm resistor. By the time you're done your overhauling, you might be 22 ohms or 21 or 23 or whatever it is. It depends on a lot of different variables, but your resistance is going to increase. So if your ohms are too high, you might trip on over voltage. So you may be okay if the application ends before the resistance gets too high, but you might not be. Okay, so what are we going to do? So let's say your minimum ohms is greater than or equal to your maximum ohms. What can I do? One thing you can do is you can choose a drive with a lower minimum ohm rating. Essentially, that will handle more amperage. So you can pick a higher horsepower drive. So if we needed a 50 horsepower drive, we could actually pick a 60 or a 75 horsepower drive. They typically have a lower minimum ohm rating, but not always. Sometimes they're the same frame size, so they're going to be the same minimum ohm rating. The other thing you can do, you can pick a different series of drive. Let's say you go to drive manufacturer A. They have 3 different series of drives. Sometimes they might have like a presidential series and your, you know, whatever the names would be, you know, your congressional series, whatever. So they might have those different series were designed differently, so they may have a different minimum ohm rating. So you can maybe go to a different style of drive with that same manufacturer. You can also possibly go to a different manufacturer. If you buy it from a distributor, they might carry different drive manufacturers. So again, they might have a different minimum ohm rating. However, there's times when you've already purchased your variable frequency drive and your resistor, and you hook everything up and it keeps tripping after 7 or 8 seconds of overhauling. If that's the case, what you can do is you can purchase an external chopper or transistor. Before, as I said, usually the transistor and chopper is internal to the drive. It'll have a minimum ohm rating of 20. If you purchase an external chopper, you can buy one that has, for instance, a minimum ohm rating of 15 or whatever it is. So you can hook up that external chopper. So now you can choose a resistor between 15 ohms and 20 ohms. So now we can pick a 16 ohm resistor. It'll work fine because it's above the 15 and it won't get over 20 when it heats up. If things are on the very ragged edge, sometimes you can adjust some of the things on your variable frequency drive. For instance, you can turn on your voltage. Your voltage turn on setting can be set a little bit lower. For instance, instead of 760 volts, it can be set at 750 or something. So it actually starts draining voltage off of that resistor a little, or off of your drive a little earlier into the resistor, and it may save you from tripping on your application. Okay, so a quick summary here of what we've gone over. Unfortunately, we had Homer pick out our dynamic braking resistor, and he chose the wrong one. So this is what you have to remember when choosing your dynamic braking resistor. You have to get the ohms right. If your ohms are too low, your variable frequency drive will trip on overcurrent. If your ohms are too high, your variable frequency drive will trip on over voltage. You have to think about your wattage. If your watts are too low, your dynamic braking resistor will get very hot and it will overheat. And of course, if your thermal switch is hooked up, it will open up and it'll cause the variable frequency drive to trip. Again, every time your variable frequency drive trips, you're shutting everything down and you're stopping production and you're losing money. If you pick a wattage that is too high, you won't have any issues with tripping. It's better to be too high and be safe. The thing you have to think about though, if it's way too high, your dynamic braking resistor may cost a little bit more and take a little bit more space. However, if you pick a higher wattage than you need, your dynamic brake resistor will run cooler, and it can also handle overloads, or if you change your application a little bit, if you have your time between cycles shortened a little bit, you should be okay. And again, remember to consider your environment when you're installing your variable frequency drives. Okay, thank you very much for attending this presentation. You will receive an email with a link to the video and a certificate of participation if you need something changed on your certificate, or if you want a PDF version of the presentation, we can send it to you. Just reply to that email. And now we're going to go to some questions if there are any.
A few questions that should appeal to a lot of our listeners today. Do all drives come with a chopper?
The answer to that is no, not all drives come with a chopper. A lot of them have them built in. So they basically take the chopper and they put it into the drive and they sell it as one complete package when you buy your drive. Some of the drives, you have to buy an external chopper. Typically, the very large drives need an external chopper and you have to buy them separately. Again, you'll have to talk to your distributor and find out if the chopper is associated with that, if there is a chopper in that drive. But typically they are, but not always. So that's a very good question.
The next question was, do all drives require a braking resistor? And their example was, for example, small matters like a 2 horsepower and I guess I'm going to interpret the question and add to it. Do all applications require a dynamic braking resistor?
Yeah, so that's a good question too. Whether you need a dynamic braking resistor or not does not only, it doesn't basically depend on the size, the horsepower of the drive, it depends on what you're doing with it. So for instance, if you are running your fan with your variable frequency drive, when you turn that fan off, that fan just kind of freewheels and it's giving energy back to the variable frequency drive, but it's doing it very slowly and the drive can handle that. It doesn't really care too much. It dissipates and it doesn't affect the drive. If you stop that fan immediately, or your application or your conveyor or whatever it is, even if it's a 2 horsepower, you're sending a huge surge of power into that variable frequency drive. That causes the DC bus voltage to increase and could trip it. So it depends on not just the horsepower. Like again, a 2 horsepower drive might need a might need a dynamic braking resistor. It may not. It depends on how quickly what you're doing with your application and how you're stopping it. Or if you want an emergency stop, anything that needs an emergency stop should have a dynamic braking resistor, typically.
Some small horsepower drives include a dynamic braking resistor. Is that correct? And if so, are they enough that you don't require an external dynamic brake?
Some of them may, but typically they won't be. Yeah, they're very, very low duty, like a 2% duty or 5. So it depends on how often you're stopping. If you stop something once every 5 minutes and it takes like half a second to stop, you're probably okay if it's internal. If you're stopping, if you're on a conveyor, it keeps going and stopping and going and stopping, and you're doing this once every 5 or 10 seconds, it will handle it the first time, and then it gets hot and it doesn't have time to cool off, and it can't handle it the second time. So that's when you need an external dynamic braking resistor.
What about continuous short accel decel cycles? So braking for 2 seconds, off for 2, braking for 2, on for 2. At what point do you need to look at this beyond being a standard duty cycle wattage application?
So if it's on for 2, off for 2, you're going to be basically it's 50% duty, whether you do this continuously. Well, if you keep going on, off every 2 seconds, that is a 50% duty cycle. So you're going to need to buy a resistor, based on your 50% duty cycle.
I think what the questioner was getting to was, in the 2 seconds it off, will it have time to cool off to ambient air temperature and therefore truly be 50% duty cycle? Or is this something where I need to consider, hey, this is closer to 75 or 100%, because if my resistor only cools off to, twice ambient the first time, then 3 times ambient the second time, then 4 times, will I eventually get into a 100% duty cycle based on the temperature saturation of the resistor?
Not, you won't go all the way up to 100 because it is cooling off a little bit, and the 100% is assuming you are braking that whole time during that whole cycle. So it's cooling off a little bit, So the temperature on that resistor after the first cycle is going to go up a little bit. It'll cool off a little bit. Second time, it'll go up a little higher and cool off. It'll essentially be a 50% rated dynamic, calculated based on 50%.
What do you consider a safe minimum ohm value as the percentage above the drive manufacturer's minimum value?
That all depends on the manufacturer, but most manufacturers give you a minimum ohm value. Let's just say it's 10 ohms. They calculate that typically by using a 10 or 20% safety factor. So if they give you 10 ohms, they're probably calculated that the maximum current is going to be something that can be handled if you have a 9 ohm resistor-ish.
And I think to keep everyone on track, we'll see if we can use the last question. You talked ambient operating temperature early in the presentation. What are some of the temperatures we're going to, like, first, what do you consider ambient operating, and what temperatures can we expect to see from these resistors?
So the ambient temperature is around 70, 75 degrees, which is typical of, most you're in your house or in your office or whatever. If the ambient temperature is up to 100 degrees Fahrenheit or so, your resistance will increase a little bit. The resistor, the actual temperature of the resistor element after it's totally saturated will rise 375 degrees around on top of your ambient. I'm sorry, 375 is in Celsius. So your ambient is 25 degrees Celsius. So you're going to have 25 degrees Celsius ambient plus 375 increase. So it'll be around 400 degrees Celsius when it's totally saturated and very hot. Again, that is the actual element. That's the hottest point that that element will get. So the air around it won't be that hot. It'll radiate, but it will get very hot. That's why, if you remember the picture of the dynamic braking resistor, it had a lot of holes in it. That's to allow the air to escape and allow the resistor to stay cool. Okay. Any other questions we haven't addressed, we will address with an email to you. And thank you very much for attending. And we hope to see you next month when we have another session talking about resistive versus reactive.